Hi, I'm Kevin Sullivan, and I'm going to be teaching you discrete math this semester. I want to welcome you to the University of Virginia, if you haven't already been here, and to my course in particular, which you've never taken before, presumably. So welcome, and I'm really glad to have you as my students. Listen, these are weird times, and stressful, and unusual, and difficult for everybody. And one of the things I wanted to tell you is if you're having any difficulties with my course, with school, with other issues, feel free to give me a call, okay? You can email me. You can talk to me in my office hours. You can contact me through TAs, and I'm really here to help, okay? So don't hesitate. And now, let's talk a little bit about this course so that you know what might be coming. Okay, here we go. Discrete mathematics is the foundation for most of traditional computer science. That's why we ask you to take a course in discrete mathematics as an early computer science student. In this talk, I'm going to cover a number of questions and discuss a number of issues, try to give you a better sense of what discrete mathematics is about, and place it in the broader context of contemporary computer science, which now includes a non-discrete mathematics subject, that of deep neural network computing. Okay. So here are the topics that I'm going to discuss for the rest of this short video. First, what is discrete mathematics anyway, and how does it relate to the mathematics that you've been studying for your entire life? The second point that I'll address is to give you a concrete example of discrete mathematics and its use to reason about some real-world situation. In fact, the example that I'm going to give you is an example of binary trees, an important discrete structure in computer science, to reason about how many ancestors you have. The topic that I asked you to think about for your little homework assignment this week. Then I'll turn to the broader context of computer science and compare and contrast two styles of thinking and two styles of computing, really. The first is based in discrete mathematics and logic, and the second is based in deep neural network computing, or, which is at the core of kind of contemporary artificial intelligence and which is responsible for major advances in our field over the last 10 years or so. And finally, I'll talk about the structure of this course, the topics that we'll cover, and some of the tooling that we'll use in order to make precise and to automate the concepts that you're going to learn in this course. So let's start with that question, what is discrete mathematics anyway? And at the risk of giving you a somewhat circular definition, I would say that discrete mathematics really is the study of discrete structures. And these are structures, which are sets of objects plus additional information about those sets. It's the study of discrete structures of these sets of objects that are discrete, not continuous. Okay, so let's briefly compare and contrast continuous versus discrete. The integers are discrete because they're separated from each other. The real numbers are continuous because between any two real numbers that are distinct from each other, there's an infinity of other real numbers. So they're all right next to each other. In other words, they vary continuously. Okay, so discrete mathematics is the study of discrete structures of objects that are discrete, not continuous in their organization. And it's the study of properties of these objects, relations involving these objects, and operations on such objects. So if we think, for example, of, let's take an example of the integers. Actually, just the natural numbers. The natural numbers are the integers from 0 on up to infinity. In other words, the non-negative integers. We'll call this set nat, short for the natural numbers. So the set nat of all natural numbers, 0, 1, 2, 3, ad infinitum, that is a set of discrete values. A property of objects in this set is that for any object in this set, let's call it n is greater than or equal to 0, right? That's what makes this a set of natural numbers. Every single number in the set is non-negative. Now consider a relation on this set, a binary relation. a binary relation compares or puts into juxtaposition two natural numbers and asserts that some particular relationship between them holds or doesn't hold. So consider the less than or equal relation. We can say that for any two natural numbers n and m, n less than or equal to m is either true or false. Okay, so given any two numbers, they either are in or are not in the less than or equal relation. We'll make these ideas much more precise as we go along. And if you're not quite following yet, don't worry. We will spend a lot of time on these ideas. And finally, an operation involving natural numbers is simply that of addition or subtraction or multiplication. So for any two natural numbers, let's again call them n and m, we can always add n and m together in order to get another natural number. So the natural numbers plus the set of operations, relations, and properties of these objects constitute a discrete structure. So we can talk about the natural numbers plus their properties, relations, and operations as a discrete structure. And of course, that's just basic arithmetic, right? So you already have a deep intuition for addition and subtraction, multiplication, less than or equal, less than, greater than or equal, greater than, and other relations on the natural numbers. So this shouldn't be, a deeply mysterious concept, although I am giving you some new language in which to talk about the natural numbers. Okay? And in computer science, we use the natural numbers all the time. For example, indices into an array are natural numbers, right, from 0 on up. Other examples of discrete structures and structures that we will study in this course include lists of objects, so for example lists of natural numbers or lists of other things. Trees, we'll talk about trees very shortly here. Sets of objects, graphs, which you may or may not know about in computer science, very beautiful field of study, the study of graphs as discrete structures. And also languages, formal languages that we use in computer science for programming as well as for specification and other computer science activities. Formal languages are discrete structures. So, for example, programs. Think about two programs written in C++. Programs don't vary continuously in a space. They are objects that are discrete. Okay? So programs are discrete. And logical expressions, and we're going to study a lot of logic in this course, logical expressions are discrete. Okay? So expressions in languages of logic, languages that we use for programming, are discrete. And in logic, expressions are generally statements that assert that some property of some other set is true or not, for example, and in order to determine whether or not such an assertion is true, we need a proof. And it turns out that proofs are also discrete structures. Right? And we'll see that as we go along in this course. So discrete mathematics in sum is the study of discrete structures, and discrete structures are everywhere in computer science. They constitute our data structures, the properties of those data structures. They constitute our formal languages. Python programs constitute a set of discrete structures. C++ programs constitute a set of discrete structures. Valid sentences in predicate or propositional logic, something we'll talk a lot about, constitute discrete structures. And again, proofs of logical propositions constitute discrete structures. So this is a course about, and discrete mathematics is about, the study of discrete structures. So what isn't discrete math? Well, most of the mathematics that you've actually worked with since about 8th or 9th grade has to do with the real numbers, and possibly a little bit of work with the complex numbers in an algebra course. And these are not discrete structures. The real numbers, as I said, vary continuously. If you take two distinct real numbers, then between those two real numbers, there's an infinity of more real numbers. And let's suppose you take one of those. Well, between it and the other is an infinity of real numbers. And suppose you get really, really, really close. two numbers separated only by this much. Well, between those two real numbers is an infinity of real numbers. In other words, the real numbers are dense. There's no space between them at all. Okay? And so the real numbers don't constitute a discrete structure. Similarly, the complex numbers, which you can think of as pairs of real numbers that have certain operations defined on those pairs of addition and multiplication and so on and so forth, those are not, the complex numbers don't form a discrete structure. And so ordinary calculus, most of algebra that you've studied in high school, Euclidean geometry, these are not subjects of study in discrete mathematics because they have mostly to do with these sets of objects that are continuously varying and dense. Okay, so I hope to have given you some sense of what we mean by discrete mathematics as opposed to, the kind of mathematics that you've mostly been studying up until now. Now, there are many different ways to give examples of discrete structures. The one that I've picked for this introductory segment of this class is the example of binary trees. Okay? And I pick it because we can use binary trees to reason about, to model and to reason about the topic that I assigned for you in your first little tiny mini homework assignment. I asked you to think about how many ancestors you have. How many ancestors do you have back exactly k generations? How many total ancestors do you have if you go from you all the way back up your family tree, k generations back? Okay? So under some idealized assumptions about biological ancestry, which in reality are not always true, but under some idealized assumptions that I'll ask you to think a little bit more about, we can model and reason about biological ancestry using binary trees. Binary trees constitute an incredibly important discrete structure in computer science with many applications. And they're not that hard to understand, as you're going to find out right now. So let's first define the set of all binary trees. That will constitute a set of objects. And then we can talk about properties of objects of this kind, such as how many elements they contain based on other properties such as their height or their depth. Okay? And then we'll use these binary trees and these properties and relations and operations on binary trees, again, to model and reason about the problem that I asked you to consider for today. So let's define a binary tree of people. And when I say define what it means to be a binary tree of people, what I'm really saying is let's define an infinite set of all binary trees of people. Now, how can we define an infinite set without writing out an infinite definition? And the answer is we use something that we're going to be calling inductive definitions. And inductive definitions are almost circular, as you're going to see right now. So a binary tree of people can take one of two possible forms, and that's it. There are two possible cases. I'm going to define this set using two possible cases. I'm going to tell you there's two possible forms. There's two possibilities for what it means to be a binary tree of people. The first case is that a binary tree of people is an empty binary tree. And we're going to use an empty binary tree to model a situation in which there are no people at all. And there's only one other possibility. The second case is that a binary tree of people can be what we'll call a node binary tree. And a node is going to have a couple of different parts, or fields, as we call them. Okay? A node binary tree contains the name of a person, or you can think of it as containing a person if you want, plus two smaller binary trees of people. And those smaller binary trees of people can be either empty trees or nodes. That's something that you need to think really hard about right now. Okay? How is it that this definition, which contains just these two very simple cases, defines an infinite set of binary trees? Well, It's that circularity in the definition where we define what it means to be a binary tree of people in terms of binary trees of people. Look at the second case. Okay, so we can model nobody at all as an empty binary tree. We can model one person as a node binary tree with two empty binary trees. We'll call those subtrees. Okay, if we want to model three people, we can use a node with two non-empty subtrees, each with one person, and having themselves all empty nodes as their, we'll call them descendants. Okay? So think about it. These two rules for how you can construct a binary tree as either an empty tree or a non-empty tree that names one person with two more trees below it, that defines an infinite set of trees. That's an infinite set of discrete objects, discrete structures, binary trees. And now we can think about, well, what properties do these trees have? We can talk about how high they are, for example, or how deep they are. We can talk about how many nodes that they have as a function of how high or how deep they are. And we can talk about binary trees all day long, and you surely will in coming courses in computer science and in this class as well. So it's often useful to represent these sorts of discrete structures graphically to help give you intuition for how they're shaped and how they can vary in their structure. So to represent an empty binary tree, we'll just use this sort of big gray dot. Okay? To represent a node binary tree, what we'll do is use kind of a structured box, okay, with three components that we'll call fields. The first component of a node or a non-empty binary tree is a person, or a name of a person. And here we represent a person as a person's name of type string. And you understand strings from other courses that you've taken in computer science. So the first field of a node binary tree is the name of a person, and the remaining nodes, which we'll call the left and the remaining fields rather, which we'll call the left field and the right field, are themselves of type binary tree of person. Okay? So that's the trick right there. You have in a node a person plus two whole new binary trees. And that's what makes it possible to fill in those sub-binary trees either as empty trees or as non-empty trees. And you can just keep going until eventually, after some finite number of expansions of a binary tree, you will have to fill in the remaining subtrees as empty trees. And in this way, you can build arbitrarily large, arbitrarily huge binary trees of people. In fact, you can represent all binary trees of people in this way. And in computer science, we'll use binary trees of natural numbers, binary trees of people, binary trees of lists, binary trees of names in a telephone book, binary trees of lots and lots and lots of kinds of things. And that leads to a notion that we will discuss later on in this course of polymorphism, where we can talk about binary trees of objects of some arbitrary type T, and now we can let the type of object in a binary tree vary across any possible type of objects that we might want to consider. Binary trees of programs, binary trees of logical expressions, binary trees of proofs. Okay, but here we restrict ourselves to the special case of binary trees of people. The main thing to understand from this example is that we can build arbitrarily large binary trees. We can define arbitrarily large binary trees inductively by just application of these two possible cases of what it means to be a binary tree of people. Okay, so now suppose let's see how we can use these ideas to model real-world situations. To model nobody at all, we'll just use the empty tree. Okay, and we can talk about properties of trees now. This is a tree that we'll say is of height 0 because there's nothing below it, and that's of depth 0 because there's nothing above it. Now suppose we want to model just you, one person. Okay, we might do that with a node binary tree. A node binary tree is a node, which you see as this big rectangle, plus two smaller trees. And the two smaller trees in this case are empty. Okay? The node represents a person, you, plus two subtrees, two smaller binary trees of people. And those both being empty leaves you with a binary tree that just represents one person. But this binary tree is now of height 1 because the node that at the top of the tree is one step up from the bottom of the tree, graphically speaking here. And this tree we can say is of depth 1 because you have to take one step from the top of the tree to get to the bottom of the tree. Okay, so height and depth are just complementary properties of a binary tree of people. Okay, so this is how you would represent ancestry, your ancestry, going just one step back. Okay, suppose now you want to model, your ancestry going one generation back. Okay, well, we use a bigger binary tree of people for that. Okay, so here you are again at the top of the tree, but now the left and right subtrees are no longer empty. Rather, each of them represents one person, namely your biological mother and your biological father. Okay? And those subtrees themselves necessarily have, each of them has two subtrees. And we leave those subtrees as empty trees because we don't want to expand this model beyond one generation back. Okay? As a little exercise, you might want to take a pause right now, hit the pause button, get out a piece of paper, and just draw a binary tree of people that represents your ancestry going back 2 generations. And fill in your own name. Fill in your biological mother's name, your biological father's name, and for each of them, fill in their biological mother and father's names. Okay? And that will give you a binary tree of people showing you your ancestry going back 2 generations. I'd ask you to go back 10 generations, but that might be hard because you'd have to draw a lot of boxes. How many boxes would you have to draw? Well, that's one of the questions that I asked you on your homework. So there you have it. Subject to certain simplifying assumptions, we can model real biological ancestry as a binary tree of people. Now, I've said before this phrase, subject to certain simplifying assumptions. That means that if certain assumptions are true, then you can model and reason about, your ancestry using binary trees of people. Maybe you can come up with an example or maybe 2 examples of violations of these assumptions. What assumptions are we making here about biological ancestry that might or might not be true in the real world? Okay, we're using these idealized binary tree representations, these symbolic representations, to represent and reason about some real-world situation. And the question is, are binary trees always or only sometimes faithful to the reality of biological ancestry? And that's a question you always have to ask, whether the discrete structures you're using faithfully model and capture the properties of the real world that you're trying to model and reason about. So see if you can come up with 1 or 2 examples of situations in real biological ancestry that might violate the implicit assumptions that we're making here when we decide to model biological ancestry using binary trees of people. So let's just assume for the time being that those assumptions are satisfied. Now we can use binary trees of people to reason about the questions that I asked you on your homework. How many ancestors do you have exactly k generations back? Well, that's the question, how many nodes are there at any depth d of a complete binary tree? And by complete, I mean that there are nodes all the way down until you get to a uniform layer of empty nodes. Okay, there's not like an empty tree here and then a bunch of ancestors over on the other side of the diagram. Okay, so if you have a complete or balanced, complete binary tree of ancestors, how many nodes are there at some specific level of that tree at depth d down from the top? Well, at depth 0, you've got 1. At depth 1, you've got 2. Clearly at depth 2, you've got 4. What if you go back down, all the way down to depth 10? How many ancestors are there? How many nodes are there? You see, we can now use the properties of binary trees to reason about properties of, real biological ancestry. How many nodes are there exactly at depth D of a tree? The other question is, well, how many total nodes are there if you start at the top and go all the way down to depth D? How many nodes will you encounter as you get all the way down to depth D? That's the second question that I asked. And so you can see that as computer scientists, as discrete mathematicians, we start with questions about the real world. We model and represent that real world using discrete mathematical structures. Those structures have properties, relations, operations. We use properties, relations, operations on discrete structures to reason about the property, to reason about those discrete structures. And then the answers that we get using discrete structures then, subject to certain assumptions, apply to the real world. And this is basically the way that mathematics works. We make a mathematical model of the real world, reason about the model, and then if we followed appropriate rules and subject to certain assumptions, we can conclude that the answers that we get should apply back in the real world. So that's how computer science actually works. What does a program do? It manipulates symbols following certain rules, and subject to certain assumptions, the outputs that programs produce we assume apply in the real world. We get answers to real questions by writing programs that manipulate discrete structures. Okay. So question for you, what mathematical formula gives you the number of nodes at a binary tree at depth D? What mathematical formula tells you the total number of nodes that you get if you start at the top of a tree and go all the way down to depth D? By writing out the little tables that I suggested you write in your little homework assignment, you may be able to just look at those tables and say to yourself, I see what the general rule is here for question 1 and for question 2. And you may be able to verify that formula works for every tree that you can write down. But the question in mathematics is usually not, does a formula work just for certain cases? When we test computer programs, we test them on a few cases. But suppose you want to know that your formula is correct for every possible value of D for depth, or every value or H of height. How could you prove that your formulas are correct for all binary trees? You want to know that some formula, some property holds for all possible binary trees, and there's an infinity of them. And yet you can't test an infinite number of trees to see if they have some property. Well, what you need is a finite way of showing that some property holds for an infinite number of possible cases. And the trick, again, is going to be some kind of inductive proof. Okay? Just as we defined the infinite set of binary trees inductively, which is using this kind of circular definition, so we are going to express proofs for infinite numbers of possibilities in a finite way using some concept of induction. Okay? And so I don't expect you to understand what that means right yet, but that's going to be one of the big topics in this course. So that's the end of my first example for you of discrete structures, their properties, relations, operations on them. Okay, and now I want to turn to put discrete mathematics and computer science and discrete mathematics in computer science in a slightly broader context. Pardon me. And so I want to compare and contrast two modes of thinking, two modes of reasoning, two modes of computation, okay, that are now both incredibly important in computer science and in understanding the world much more broadly. Okay? Daniel Kahneman wrote a book for which he's quite famous now called Thinking Fast and Slow. Kahneman was a Nobel Prize winner. And the two modes of thinking are what he calls fast thinking and slow thinking. Fast thinking is, an example of fast thinking maybe is you see a snake out of the corner of your eye and you just jump. Okay? You don't have to go through any logical reasoning to jump. You don't have to say, I see a snake, what should I do when I see a snake? I should conclude that I might be in danger and therefore I should jump. That's not how it works. You know that's not how it works, right? You see something out of the corner of your eye, a spider, a centipede, a snake, and you just jump, okay? You feel something crawling on you, you just jump, okay? That's fast thinking. That's hardwired thinking. It does not have to go through the symbolic reasoning systems of your brain. Okay, and lots of creatures, of course, think this way. They respond to stimuli in this way. They respond to their sensor inputs. If you think of your eyes as sensors, then your eyes are hardwired into certain circuits that just do what they should do fast, because if you didn't evolve to have that kind of thinking, then you would have gotten bitten by the snake and you maybe wouldn't have survived. So we have evolved systems of fast thinking, and so have many other creatures. So here I have down in the lower left corner of this slide a little video, and you can find lots of cat and cucumber videos on YouTube. I don't recommend you do this to your own cat, but here's a pretty little kitty, and it's happily eating its food, and then it looks adoringly at its owner and doesn't see the cucumber behind it, and then it sees the cucumber and it is scared as heck, and it jumps and runs away. That's fast thinking. Okay, that cat did not go through any kind of rational step-by-step thinking process in order to respond to that cucumber. On the other hand, in this course, and in the way that we just reasoned about ancestry, we clearly went through step-by-step, rigorous, absolutely precise kinds of reasoning about, what formulas apply to describe, how many nodes are in a tree, and we're going to use binary trees to model people in the world, and we're going to use properties of binary trees to draw conclusions about how many ancestors you have going back a certain number of generations. That's slow thinking. Now, most of the computer science that you've learned so far is about slow thinking. What are you doing when you write a computer program? You're writing a step-by-step, logically deductive process that, when started with certain inputs, goes through a kind of, step-by-step logic and finally produces an output that you interpret generally as having some meaning in the real world. And we also think this way. When we sit down to analyze a problem and figure out how to solve it and come up with a step-by-step solution, that's slow thinking. So I would like to strongly recommend to you that at some point, maybe even now, for pleasure reading, you pick up this book. I think you can get it for under $10 on most of the auction sites. Thinking Fast and Slow by Daniel Kahneman. So where does fast thinking come into play in computer science now? Well, some people argue that the area of artificial intelligence involving what we call deep neural networks approximately models fast thinking. And so the idea here is we have huge trees of very simple circuits, each with certain coefficients. And when we run lots and lots of data through those circuits, look at how the outputs mismatch reality and then adjust the coefficients of those circuits. If we do that over and over and over and over and over again, then we drive those circuits into configurations in which they actually begin to behave in ways that we might expect. So for example, if you give a circuit a picture of a cat as an input, maybe it says, that's a cat. But if you were to give it a picture of a dog as an input, it would say, oh, that's a dog, with 99% probability. Okay? And so deep neural network and related forms of computing, which have revolutionized artificial intelligence in the last 10 to 15 years, based on ideas that go way back to the 1950s, this form of computing is really not about discrete structures and logical deduction. It's more about that kind of fast thinking that goes on in many natural systems. Okay, so to put another point on this discussion, I want to talk about symbolic reasoning, and by that I mean step-by-step logical deductive reasoning. We use abstract symbols and rules governing them, their properties, relations, and operations, to model and reason about real-world domains. We use binary trees, which are kind of symbolic objects with string names and subtrees as fields, to model and reason about biological ancestry, and we used formulae describing the numbers of nodes in binary trees, well, you come up with those formulae, to obtain answers about biological ancestry. So again, symbolic computing, symbolic reasoning, logical deductive reasoning is the foundation of most computer science and traditional AI, but not of the new field of, or newly invigorated field of neural network computing in artificial intelligence. That's a different kind of thing. So in this course, we focus on discrete structures, symbolic reasoning, and this is complementary to deep neural network computing. We study computational structures as well as logical structures. Computational structures are things like Booleans and Boolean algebra, natural numbers and ordinary arithmetic, lists where we can talk about lengths of lists and operations like appending to lists, trees we've seen here, and inductively defined data types more generally. A really cool fact is that formal languages like logical languages and computer programming languages are themselves just discrete structures, and we can use the lessons of this class to define and reason about languages. Okay, so that's pretty cool, and in this class we hope to have time enough for you to define the syntax and the semantics of a few small languages. Okay. Logical structures, sentences in predicate and propositional logic, are also discrete structures, and so are proofs. Okay. As a final point, in this class we take not just a paper and pencil, but a computational approach to learning discrete mathematics. You want to be great computer scientists? Okay, let's use a modern computational logic tool to automate and make very precise the ideas that we'll cover in discrete mathematics. The tool that we'll use this semester is called the Lean Prover. There are other tools like it out there. They're becoming increasingly important for in fields such as provably secure computing systems. Okay? And in the next video, I'll address getting yourself set up to use the Lean Prover tool starting this semester. So in summary, we've answered the question, what is discrete mathematics? In brief, it's the study of discrete structures, their properties, relations among discrete structures, and operations involving discrete structures. We gave an example of using binary trees of people to model and reason about ancestry. We put this form of reasoning and computation in context with deep neural computing and contrasted sort of fast and slow forms of thinking. All of the traditional computer science programming in Python or Java or data structures, the usual courses in computer science are all about discrete forms of computing. When you get to your third and fourth years, you may take courses in artificial intelligence, and it will probably take you until a second course in artificial intelligence before you really get into the field of deep neural networks in any serious way. Okay, so the focus of this course is on a broad range of discrete structures with particular emphasis on things like natural numbers, data structures like lists, logical and other languages as discrete structures, and on proofs as discrete structures that we can use to show that certain logical propositions are true, subject to certain conditions. Okay? In the next video, we'll give you an introduction to and get you started on setting up the Lean Prover tool. So that's it for now, and stay tuned for the next video. Again, I'm really happy to have you in this class. And again, if you have any issues, feel free to contact me, okay? I will even come and meet you properly masked and socially distanced if we need to talk in person at some point. Okay? All right. Good for now. Bye.